third final lecture about this course.
Thanks. So last time, just a quick recap. We found a current in this cohomology class, which was a Taylor current, something like, I don't remember what I did. Let's say it's beta times chi, yeah? And our aim was to regularize this current using convolution locally and then patching up these convolutions carefully, yeah? So to this end, we covered the manifold up with balls of radius 2r in such a way that the balls of radius r continue to cover the manifold. And on these balls, I mentioned it's precisely the last time, but basically chi is close to Euclidean. And then even the potentials of chi are close to Euclidean and so on, right? Chi is del bar of P naught. This is close to Euclidean. Likewise, this, there is no real restriction on what this is, but it's just this. And then T is omega plus del bar Ct, which is locally this, yeah? So what you do is then you convolve this to smoothen it out, not quite just, not just this, you subtract off a little bit of this, and then you convolve. You don't have to do this, you can convolve it even before, but might as well, right? So you take this convolution, right? Now, the point is, you define this function as, let's call this, let's give this a name, Phi delta minus P tilde naught, so that it's it lies almost in the correct class, so to say, right? Except for this, if this was not there, this is more or less like phi t, some regularization of phi t, right? On this ball. And minus infinity elsewhere. Okay, so now we have a globally defined collection of functions. And what we want to do is we want to say, define P reg as the regularized maximum of all the Pi's. This is what we want to do. Okay? Ideally, we want to say that this regularized maximum is a smooth beast. And if you take this plus this, we want to say this is scalar. This is what we would ideally want to say. The problem is, when will this be smooth? When does the regularized maximum entail? It entails adding a bit to each of these and then taking the maximum of those and then averaging out these things, right? So in other words, if outside, let's say, a ball of radius 8 by 5 divided by 5 plus some hi does not contribute to the regularized maximum, then P reg is smooth. And all that we hope for will work. And this is the challenge. Okay? This would have been correct. This would have been correct had this been a continuous function. That's precisely Ricberg's regularization argument. The problem is this is not continuous, right? But as we discussed the last time, the idea is to use Lelong numbers. Once again, I'll just write down very quickly what's the delta Lelong number. Sorry, what am I calling these nu of x delta t is defined, nu x delta and phi, and say, let's say phi is defined as the supremum of over a ball of radius r by 4, supremum of a ball of radius delta, and natural log r for natural log delta. Okay. These delta Lelong numbers converge as delta goes 0 to the usual Lelong number of, let me say, p, okay, at a point x. And Sew's theorem guarantees that places where this Lelong number is, say, larger than a fixed value, this is a subvariety. It's an analytic set, but let's pretend it's a subvariety. Okay. This is the subvariety EC. Now, what I'm going to assume is there is a smooth function C such that omega plus this is scalar, right? And over here, the Lelong numbers are very small. Here, the Lelong numbers could potentially be large, okay? And we want to apply this Rydberg kind of regularization to this entire beast. So to this end, there is this crucial lemma that I was attempting to write the last time. So this lemma was due to Gaussian. Let's keep this here, a proposition, if you will. So let some constant, don't worry too much. This is some constant that just depends on n. I won't write down what it is. For delta less than r over 20, the following hold. Okay. If the Lelong number, if at this point, these Lelong numbers are all very small, then I'll just write this down and I'll explain what this really means. I'm sorry, I know it's quite a mouthful, but it's saying something very reasonable behind all this language. And lastly, if the Lelong numbers are all very small, then you can patch these using the Rydberg method. Then the max 9r over 5 if minus 8r over 5. Right. Okay, so this is quite a technical little statement, but it's saying something very pleasant, saying the following. If you take a point x, right, let's say it's contained within a few balls, it's probably close to the boundary of some balls, it's very close to, it's very much in the interior of certain other balls, right? So let's say if the maximum value of all these Lelong numbers in all the balls that it is in is very small, right? Then what happens is this holds. What does this mean? Let's just draw this picture again. C is defined here. Here the Lelong number is small. Here it could potentially be large. So suppose you are near the right. So if you're near this boundary, C must not contribute to the maximum. If you're here, right, you're taking a bunch of maximum of a certain bunch of functions. If you're near this boundary, this must not contribute to the maximum. That's the principle. If you're near the boundary of a place where a function is defined, that function must not contribute to the maximum. Okay. Now you're near the boundary of where C is defined, but C is smooth. These things, okay, you've regularized them, sure, but the point is, as the regularization parameter goes to 0, these things become singular, but this still remains smooth, right? So the trick here is, when the Lelong number is so, this means these phi's are roughly log mod z square. Okay? Meaning, once you regularize, what happens, these phi deltas, they roughly behave like this, 2 epsilon 2 natural log delta. Now, what I'm doing is, I'm adding 3 epsilon 2 natural log delta to this C. So when you're very close to the boundary, what happens is, this is highly negative, but it's not as negative as this is. That's why these things, they dominate this here. Okay? That's what this is saying. If your Lelong number is small, right, then ideally at these places, presumably the Lelong number is small. At these places, this does not contribute to the regularized maximum. That's what this part of the statement is asserting. This part of the statement is asserting, if you go very far from here, if the Lelong number is small enough, right? Again, this point is in the interior of certain balls, it's near the boundary of certain balls. The boundary parts do not contribute to the regularized maximum. These are the interior ones, if you wish. These are the places where X is close to the boundary. Yeah? This is somewhere in between. Okay? This is saying that if the Lelong number is very large, if you're very close to this place, then C will dominate. That's what this is saying. It's saying the opposite. It's saying if blah happens, then the Lelong number is small. So in other words, if the Lelong number is large, blah does not happen, right? And the blah talks about the infimum of C, right? So in other words, C will dominate where the Lelong number is large. That's the crucial part here. This proposition, C is smooth. Yes. Excellent. Yes. So once we have this, the patching up works, and all that is nice and true in this world will be preserved. Okay. So that's the point. And notice that this is a very reasonable sort of a proposition to expect if you pretend that a singular function phi, if you regularize it, it looks roughly like the Lelong number times log delta. If you pretend this, if you pretend that phi is exactly log mod z squared, this is perfectly reasonable. Okay? And this is just saying that phi's behave like this, right? Okay. All right. So now our whole problem statement has been reduced to finding this C, right? So this is the last part of the proof. Finding C. Okay. Let Z be a subvariety. We want a smooth C such that in a neighborhood U of Z such that this is a Kähler form. Okay. So Z is any subvariety and we want this to happen. If Z is smooth, then this is trivial. Why is it trivial? Because if Z is smooth, notice that we have not yet used the fact that the integrals are all positive. This has not yet been used, right? If Z is smooth, then if you restrict this cohomology class to Z, these criteria will be satisfied here. So by the induction hypothesis, there exists a smooth, let's say there exists a smooth C tilde on Z such that this is positive by the induction hypothesis. Then what do? You simply take this plus, what am I calling this? A. Distance squared from Z for large enough A, this will be a Kähler form. This in a small enough, I mean, what do I mean by this? I'm abusing a notation, a bit. What I should be doing is C is a priori C tilde is defined here, but by the cubular neighborhood theorem, there is some neighborhood and some projection map which is not holomorphic to this, right? While it is not holomorphic, if you're very close to Z, it is approximately holomorphic. In other words, my point is, this works. This satisfies this. This satisfies this result, this requirement, provided the neighborhood is chosen to be very small, okay? Such that this is smooth, and this makes sense, and so on. So this is easy. Now the problem occurs when Z is singular. If Z is singular, okay, then what should we do? Obviously, we need to resolve the singularities. Oops. Something like this, maybe. Right. So you resolve the singularities using Hironaka's result. Yeah?
Do you use Y to use T, but Z is somehow...
Z is any arbitrary subvariety. This is, it's the Lelong sublevel set. It's the place where the Lelong numbers are large.
That's fine. Yeah, you started with picking a Y.
Yes.
But you need other subvarieties than Y as well. So, of course, you need that to
yes.
Can't just have this thing for Y, but this is where that comes in, that you don't really have control over what Z is.
Yes, you're right. You don't have any control over what Z is. You're absolutely right. It's true. Unlike Y, yes. So if Z is singular, then this thing doesn't quite work. I'm lying a little bit because it can be made to work if you do induction cleverly enough and you use some other tools, not. By the way, just to be clear, this is not how Demay and Pon proved their result. This is not their argument. I've just adapted Gauchens and Wade's and our arguments in this setting. Okay, they do it slightly differently. Okay? This is a very deep idea. Okay? Anyway, so here you resolve the singularities. Hironaka's resolution of singularity says that you can blow up finitely many times along smooth submanifolds and get the proper transform will be smooth, right? But the point is, let's assume for the sake of argument that you blow up only once, okay, just for illustrative purposes. Then what do? Okay. You have this. So if you take this is not expected to be a Taylor class, obviously, right? You expect it at most to be semi-positive. So what do? You take some omega tilde, let's call it omega tilde epsilon, which is the pullback of this, minus a small multiple of the exceptional divisor E, right? This we expect it to be Taylor. Now the point is, I claim the following, that if you take this is larger than chi tilde raised to p, where chi tilde is pullback of chi plus epsilon tilde times FH. Okay, right. So what is FH? The exceptional divisor defines a line bundle. You put a metric on the, notice that that line bundle, when restricted to the exceptional divisor, is just the O-1 bundle, right? So you put a metric on that line bundle that is negatively curved. It's sort of an extension of some negatively curved thing here. So if you take such a special metric, then this will be Taylor, right? This is how you produce Taylor forms on blow-ups anyway. The claim is this is true for all small epsilon. Okay? Why is this true? This is where we need this uniform positivity condition. Because what happens here, how do you calculate this intersection number? So how does one calculate this intersection number? What is this intersection number after all? You take pi star omega. Actually, maybe I should put a minus here, not plus. Maybe. Right. Sorry. Yeah. Oh, I see. I see. Yeah. Right. Thanks. So what do we have here? Right. This one raised to p. So when you want to calculate this intersection number, so if v tilde was completely contained in the exceptional divisor, this would be trivially positive because this doesn't even occur and this is just like O1, right? But on the other hand, if v tilde does intersect the exceptional divisor, then you can pretend that this is simply, you can go downstairs, you can forget this measure zero thing, right? And just go downstairs and integrate this, right? So take the push forward, if you so will, in some sense, because it's an isomorphism away from this, and you can integrate this. Now, the problem is, while this is, what's this integral? It's like omega raised to p plus blah, blah, which is at least of the order of epsilon tilde. And this could potentially be negative, right? So if you only knew this was positive, you would be in trouble. Okay? So if you knew instead that this was larger than, it's too many epsilons, but okay, if you knew this was larger than this, now there is some hope, right? We can hope that if epsilon tilde is very small, this plus this is still larger than, let's say, epsilon over 2 times this, right? This is the hope. Is that true? I'll come to it in a moment. That's true. But once you do that, let's say this is true. This needs clarification. Then, in this class, you will have produced a Kähler metric, right? So you will have produced some sort of a Kähler metric in this class. Some C tilde is positive. Okay, so you would have produced a Kähler metric. Then you have to somehow come downstairs and bring the Kähler metric downstairs. That's also not trivial, right? Now, from this to downstairs, and the clarification required here, these two rely on one neat trick. Okay, this was originally due to Demain-Pon. The idea is this. Let's go back here. What did we blow up after all? We took Z and we took some thing here and we blew this up, right? This is pi of the exceptional divisor. The point is this has it's a lower dimensional subvariety and it's smooth, meaning there is a neighborhood downstairs here. There is a Kähler form in this neighborhood, okay, by the induction hypothesis and the previous construction by adding a large multiple of distance from this thing squared. Okay, so there's a smooth Kähler form, omega plus some C2, for example, here. Okay, so what you do is the following. Suppose you manage to produce this. What you do is you take this plus a small multiple, let's say some epsilon double tilde, ln mod S square. Okay, and take the regularized maximum of this and maybe this plus a large constant. So what you're doing here is this C tilde, the push forward of C tilde. So, or yeah, maybe you can do it upstairs as well. So what you do is you take C tilde, which is a priori a nice thing away from this submanifold, right? And you add to it a small multiple of this. How does this help? It helps because if you add this small multiple, then this goes to minus infinity here. So it will not contribute to the regularized maximum. And the smooth thing, C2, contributes to the regularized maximum here. Okay? And in case you're wondering what happens to this, notice that away from this locus, the line bundle is actually trivial. Away from the exceptional divisor, this is actually trivial. So in other words, this doesn't contribute anything to cohomology when you take the push forward downstairs. All I'm saying is this is del bar log h, where you have a trivialization. I mean, this is a globally defined function away from the exceptional divisor. So that's the idea. So you patch these two up and you get a smooth thing downstairs. And to prove this, to prove that this is larger than epsilon over 2 times pi raised to p, you do the same trick. You find a representative of this class that is Kähler in a neighborhood of the exceptional divisor by using this patching trick, and elsewhere it can be whatever you want. Okay. Once you do that, then it's easy to prove this. This point, one can do this as a calculation. You break this integral up into 2 pieces, one piece near this, one piece far away from this, and so on and so forth. Okay. Right. So this is the basic idea of Gauchen et al. Applied to the Demain-Pon situation, a weak version of it. And where did we need the uniformity hypothesis? Precisely here. Okay, this is where we needed it. This is where Gauchen needed it as well. Now, Wade and I, and later Jian and we managed to remove this uniformity hypothesis. Our key idea was the following, that you remember concentration of mass, that is the ability to produce a Taylor current in an F and big class. We did this concentration of mass in this class. So we produce not quite a Taylor current, but a current that is larger than a multiple of the pullback of a Taylor form, more or less. Not, in fact, we managed to concentrate mass on the pullback of an ample divisor, so to say. Okay, that was enough to make certain arguments go through. Then the idea was we perturbed this exactly like this, but with some control over this perturbation constant and so on and so forth. Okay. Right. So now I'll go to the J equation. Yeah.
Are you saying that you're sort of choosing epsilon tilde regardless of what E is? Or
yes, that's key.
Yeah.
Nothing should depend on V. Okay. So if you were to, if
that's kind of saying
right,
then that you get some uniform lower bound on the Seshadri constant somewhere.
So
because you're saying that this then, okay, if you knew that you started with a Caylor class, then you're doing something to say that, okay, this is Caylor on the blow up.
Yeah.
I think.
This is Caylor on the blow up.
Right.
Yes.
Yeah. So then if this epsilon tilde is chosen independently of E,
yes,
it's kind of giving a lower bound. So then this epsilon tilde that you choose is smaller than the Seshadri constant of E.
The epsilon tilde will depend on epsilon, if that helps.
Yeah, but yeah. So you start with your class omega. You then get an epsilon, and if you knew it's Caylor, then you know this uniformity.
Yes.
And then this stuff.
Yes.
And it shows that you can then choose this epsilon tilde independently of
V. Yes.
Which then gives you a uniform lower bound.
Yes.
It seems to me that you get that.
Maybe. Honestly, I don't remember what the Seshadri constant is.
Yeah.
Let's see. Okay. Yeah, I don't know much about the Seshadri constant.
The Seshadri constant is for blowing up points.
No, I mean
you can define it.
You can define it for arbitrary.
Yeah, I mean, I guess my point is that when you just consider points, it is true that you can find a uniform lower bound.
Yeah.
And I don't know whether that's true for higher dimensional subvarieties, but I guess implicitly it is true as well. But for points, at least, it's a kind of true fact that you can take the like Seshadri constant independently.
Yeah, there you can see it. I mean, it's somehow related to the size of how big of a holomorphic normal coordinates you can choose. So for points, you can see it like that you get a uniform thing.
Here
it was more related to what you're showing.
I see.
Something that seems to be true.
But like the question is about, I mean, it's not obvious that if you start off with a Taylor class and you blow up a submanifold the same, then for any possible submanifold, there is an epsilon such that the pullback of
it's not obvious.
Minus epsilon E is actually Caylor on the blow up. Like that's true for a fixed submanifold.
Yes.
You're saying that that's true over all submanifolds. That's kind of a normal.
Right. So the proof is also not obvious. What you need to do is you need to choose a special representative of this class. Namely, for this, you choose the curvature of the bundle, right? And then for this entire class, what you do is you do this gluing trick to come up with a representative that's Caylor in a neighborhood of the exceptional divisor and outside its smooth. So when you write this integral up and you break it up into two pieces, one in a neighborhood of the exceptional divisor, where this is Caylor, so it's positive. Away from that neighborhood, what happens is, if you choose any representative of this will be controlled by omega, because outside that neighborhood, this thing is uniform. This is Caylor. right? So it dominates this. Okay. So there you can choose that epsilon tilde to be so small that, I mean, pointwise this can be this is dominated by a representative here. That's roughly the idea. I mean, basically, what kind of terms appear here, right? For example, you'll have something like this. Let's just do this, right? So you'll have something like this, raised to p minus 1, right? Let's say choose some neighbor, some representative, you'll get something like this. The point is, this FA is less than some constant times pi star omega away from the exceptional divisor. So this is less than sorry, pi star chi. Right? And this, whatever it is, it's certainly less than some other constant times pi star chi raised to p, right? This is bounded by this. So that can be absorbed into this. That's the idea. Okay? So this is only away from a neighborhood of the exceptional divisor, right? And in a neighborhood of the exceptional divisor, this is positive anywhere. That's the idea. So you come up with a nice representative of this class.
I think perhaps what you're asking is a stronger version of why it's true that having a Taylor class means that the strong uniform lower bound on the integral over d of omega to p is bounded below by epsilon times the integral over d.
Yeah.
That again is
That's
basically like very similar question. I think your question would imply
yeah. I mean, if you knew that the omega was Kähler already, you wouldn't need this with the epsilon.
Yeah.
You didn't need chi.
Yeah.
But it's proving something similar, but on the blow up, I have to say.
So there is a, I'll just talk about the J equation for a few minutes, but a similar step in the J equation would require you again to choose a nice representative that satisfies some nice condition here, and outside this, it doesn't have to. Okay, that's one more idea of Gaussians. Okay, right. So let's deal with the J equation now. The last half an hour or so. Okay. So firstly, recall that if you take the Mabuchi-Yao energy functional, whose critical points are constant scalar curvature Kähler metrics, you can, thanks to Chen, you can write it as a sum of three things, where there's the so-called entropy. And this is one functional. I won't write the formula for the I and J functionals. The key point is that this entropy is always bounded below, right? So if this thing is bounded below, then the K energy would have been bounded below. In fact, one can prove that. So we want this to be bounded below. Now, if you take any two Kähler potentials, there's a geodesic connecting the two. Along that geodesic, this base is convex. So if it has a critical point, then it's bounded below, right? So we want to find critical points of this thing under the condition that C1 is less than 0. Only then is this convex. So if C1 is less than 0, then this is convex along geodesic. So if it has a critical point, it's bounded below. And then you can hope to find constant scalar curvature Kähler metrics. So the critical point equation of this functional is a special case of the J equation, which is this PDE. Okay. So notice that if you write pointwise version of it, if let's say chi is Euclidean, and if let's say omega phi is, you diagonalize this, then this boils down to this. In other words, it's an equation in the inverse of the Hessian of P in some sense, right? Okay. Now the point is because this is a Kähler class, that means at least at one point all the eigenvalues are positive. Okay, why? Because by the maximum principle, if you take the minimum of phi, there this is positive. Okay, so this is larger than omega. So at least at one point, all these eigenvalues are positive. So if you take any other point and you connect them by means of a path, the first time one of them becomes zero, you have a problem here, right? So any solution to this must be Kähler, point one. Point two, if you take any solution to this, it satisfies this obvious inequality. If you leave out a few terms here, that is, if you only keep a few terms in the summation, this is obviously strictly less than NC. In other words, if you take any solution, this expression will be strictly less than NC. So here's a necessary condition to solve the J equation. If you can formulate it in this setting, necessary condition is this. There exists a representative that satisfies this property, this pointwise property. This is exactly the same as saying that if you take the sum of 1 over lambda I for an index which is of size n minus 1, then this is strictly less than NC. Okay, this is exactly the same as that, right? So this is the so-called Cohn's condition or the subsolution condition. I don't like using the word subsolution because that would remind me of something like this. This is what I would have liked to call a subsolution. That's why I call this a Cohn condition. Okay? Right. So subsolution, what's a subharmonic function? This, right? So you take the right-hand side and you make it an inequality. So I would have said that subsolution would have been this. You just make this equality into an inequality. This is markedly different from that.
So why did Song and Weinberg use? I mean, are they the ones who started calling these things subsolutions?
I don't know who called it subsolutions, but they're wrong. But I mean, honestly, the literature is, some people call this, I mean, I think Tristan calls it the Cohn condition. Yeah, I don't know. At least in our paper, we called it the Cohn condition just to distinguish from this. That's all. Anyway, so the conjecture here is the following. That is, conjecture is, if Sure. But the bottom line is it's equivalent to the equation with the equality replaced by an inequality, right? So, for example, Tristan calls one of these sorts of things as C subsolution. I think that's what, if I'm not mistaken, that's what he calls this, right? C subsolution. Anyway, terminology aside, so let's go back to this. So the conjecture is, if this is true, that means there exists a representative satisfying this. What was known prior to Gaussian was this implies that the J equation has a solution. This is thanks to the work of Song and Weinberg. So this was the conjecture. What Gaussian proved was this. Okay, this was what Gaussian proved. Then we improved this result. Okay, so what's the difference between this and Demey and Pont? The method of proof is similar, but again, what's the method of proof again? The two main steps. One is concentration of mass. The other is regularizing. Okay. Right. So what does this step entail? It says, again, what's the method of proof again? You take omega plus t chi for large chi, for all t greater than or equal to 0. Right? Where again, m is projective, right? In this talk of mine, m is always projective. Right. So for large t, obviously this has a representative that meets this criterion, right? I mean, after all, this has a larger power than this, right? It scales well. Okay. And the set of all t for which this has such a representative is obviously open. So again, without loss of generality, let's assume you have a sequence converging to 0. The aim here is to produce a current in this class. That's firstly a scalar current. Might as well say omega. Secondly, it satisfies this thing. I'm lying a little bit here, and I'll tell you what to do it here. This is a very problematic requirement. Why is it problematic? Because you cannot multiply distributions together, right? You can't multiply currents. So what the hell does this even mean? Second point. Actually, in this regularization business, you lose some positivity when you do Richenberg regularization. Why? Because you have to subtract a little bit to make sure that near the boundary of any ball, this function does not contribute to the regularized maximum. So what you need here is not a current in this class, but in a slightly smaller class. Okay? So this, in my humble opinion, was a very bold idea of Gaussian. He did what would have been natural, but a slightly scary thing to do in the sense that you wouldn't know whether it's well defined or not. What he said was the following. So the definition of this, let's get the, sorry, yeah, my notation with it here. Right. So the definition of this is for any coordinate chart U, if T is square root of del bar phi on U delta, U is something, U delta is this, then if you take the convolution of this current, one small problem here. If you take the convolution here, this is a nonlinear expression, right? And this is also not constant. So how do you deal with that? Again, there's a remarkable idea of Gaussian here. He replaces it by this constant coefficient form where chi naught is any constant coefficient form satisfying this on dx delta. So what's the meaning of this phrase? What's the meaning of this? Right? This means if you take any coordinate chart where this is del bar exact, right? Then on U delta, that is on this set, which is delta away from U, the convolution of this current satisfies the cone condition, except I mean, I want to multiply this by 1 minus epsilon because I want a slightly better cone condition. I want this to be uniformly positive in some sense. And more crucially, okay, actually what so what does this mean to be strictly positive, right? Maybe if I had said non-negative, I wouldn't have needed the epsilon, right? Now, the crucial part is this has to be replaced by a constant coefficient Taylor form so as to not interfere with any of the convolution properties, where this constant coefficient, this holds true for every constant coefficient Taylor form that is less than your original Taylor form. Now, if you make such a definition, you have a sanity check is to check whether this is correct if T was smooth, right? Now, if T is smooth, and if this is genuine, so the first property you note here is monotonicity. If this is true, then this is certainly true if you reduce your Taylor form a bit, right? Obviously, it's a negative contribution after all. That's why you need this. Second point, if this is true, why is the convolution of this true? Notice the convolution is if you take the product of two things and the convolution will behave horribly, right? But herein lies a beautiful property of the J equation. This is equivalent to saying that this is less than what? NC or N minus 1C for all. This is equivalent to this. And A goes to trace of A inverse is a convex function, right? So since it's a convex function, what is convolution after all? It's a weighted average, right? So the convexity plays well with this weighted average, and it allows us to conclude that if T was genuinely smooth, this would have been true, okay? And if this is true, if T is smooth and this is true, then this also has to be true. Okay, why is that true? I'll leave that to you as an exercise, okay? So this is a well-defined notion of the cone condition for currents, okay? So even this definition required a little bit of justification, right? One more point, a property that this satisfies this is if a sequence of smooth things converges weakly to a current, and if these things satisfy this, the limit will also satisfy this. This is also easy to check. If a sequence of smooth things converges weakly to this, if these things satisfy this, right, then the limit, the weak limit also satisfies this. The reason being, what is a weak limit after all? I mean, the convolution is basically testing a current against a smooth function, right? And what is a weak limit? You test this against any smooth thing that converges to this tested against the same smooth thing, okay? So this property is preserved under weak limits as well, right? Now that we have defined this, how does one prove it? How does one prove that this sort of a thing exists? You have to solve an appropriate PDE, obviously. What PDE must you solve? You solve this. Actually, might as well put C here. Where Ft as T goes to 0 puts mass on an ample smooth divisor Y. Okay, just as before, right? So you solve this. The only slight complication is Ft is allowed to be slightly negative. If you construct what that Ft is, then it will turn out that you have to allow it to be slightly negative at certain places. And as far as PDE results go, if this were positive, Then existence for this PDE was known earlier, thanks to, I think, Collins and Zekilhidi. But if you allow it to be slightly negative, you have to reprove that theorem. That's what Gaussian did. Okay, so that PDE part, but that's standard. I mean, you just use Yao style estimates and it'll go through. And point is, if you take a sequence of these omega n's, they converge weakly to a current T. That current, if you follow Demey and Pond's arguments, you can see that that current indeed satisfies the cone condition and puts some mass on the ample divisor Y. Okay. Now, what do? Exactly as before, you would, let's make it 2 beta. Okay. You subtract this off. Right? Then, this is larger than a Kähler current. This is a Kähler current, right? The only slight complication with this process here is notice that now this beast will put a lot of negative mass. So what happens is, we know this satisfied the cone condition. What does that mean? You take the convolution of this and that satisfies certain inequality. The problem is if you take the convolution of this, then you'll be in trouble here. So in other words, this operation might be problematic cone condition wise near Y. In other words, this, if you take the convolution of this, this does not satisfy the cone condition in a small neighborhood of Y. That's a problem. Okay. So in the regularization part, again, how do you do regularization? It's exactly the same procedure as before. You cover the manifold with balls, you take convolutions, you take a place where the Lelong number is very large, you come up with something in a neighborhood of that satisfies the cone condition. Away from that, the Lelong numbers are small and you do this Richenberg patching up argument. It works. The problem is, here, we had to prove an additional lemma that stated that the Lelong number is uniformly large in a neighborhood of this, in a 5 delta neighborhood of this. We had to prove this little lemma that ensured that despite the cone condition not being satisfied by this near Y, the smooth thing will this will not contribute to the regularized maximum in a 5 delta neighborhood here. We need that, okay, to make sure that the cone condition is met throughout. Okay, so this required a technical lemma. Then I proved. This was only an artifact of our paper. Gaussian does not need this trick. He directly proves that there exists a Kähler current that satisfied the cone condition. But his proof was complicated. It was modeled on Demey and Pond's proof, but it required some very ingenious tricks that we didn't have to use. Okay. So then you do regularization again, but maybe a step between these two is the induction hypothesis step. That is, if you have a subvariety Z, then do you have a neighborhood around the subvariety and a smooth function such that this satisfies the cone condition? This is the crucial step. Everything else follows more or less similar to what we did earlier. This is the one that requires some work. Again, if Z is smooth, this is trivial. Again, as before, you add a large multiple of the distance squared. If Z is singular, you take a resolution of singularities. Now you need the uniform condition, because now what you want to do is you want to add a small multiple of the exceptional divisor. And you want to prove that this beast continues to satisfy those integral conditions, right? That I've erased, okay? This requires some work, and this requires uniform positivity. And again, as in Demey and Pons approach, I mean, in that theorem, near this exceptional divisor, you choose a nice representative such that near the exceptional divisor, it satisfies the cone condition. And far away from it, it's just scalar. Okay, so you choose that representative to calculate the integrals, and you prove that this continues to be uniformly positive. Therefore, this admits a smooth representative satisfying the cone condition. Then you patch it up with the smooth, with a smooth representative in a neighborhood of this, right? And you get this. Okay, that's the idea. So this was Gauchen's idea, that you come up with smooth thing here and then you patch things up. How do you get rid of this? How do you get rid of the uniformity? How do you get rid of this epsilon there? Again, as I said, what Wade and I did and what Jian Song did was we proved something slightly stronger. We proved a degenerate version of concentration of mass. That is, instead of coming up with a Kähler current in a big NF class, we came up with a current in this class that put some mass on the pullback of an ample divisor, basically. Okay. Once we did that, we could somehow carry these arguments through. It's a technical thing, but worked nonetheless. Right. Sorry, I'll stop. I'm lying a little bit. This is not the class to consider. You perturb this also. You add 1 plus a little bit here also. But that's a technicality that I didn't want to get.
The convexity thing.
So
the operator is sending A to trace the inverse A convex.
Yeah.
So in other problems, is that somehow the key insight for like the supercritical transmission angle?
Yes. This convexity. Yes. The convexity is important for various reasons. Here the way I use it here was to do the convolution business, right? But even to prove estimates in Yao's approach and so on and so forth, you need this convexity. I mean, how do you prove estimates, right? You differentiate the equation twice, you come up with some nice function, you differentiate that twice and say at the maximum it's less than 0 and so on and so forth, right? Then you make sure that the highest order derivative terms of the things you differentiated and the things that your equation gives are, they match up. Then you have lower order terms to deal with, and they have to be dealt with using convexity of this sort. So for estimates, it's crucial that you, even for higher order estimates, I mean, Yao gives you only second order estimates. To get higher order estimates, you have to use Evans-Krylov theory, and that requires convexity of this sort again. So it's a very important thing to have convexity.
The confirmation in this case is that up to starting the process, is the strategy really the same?
So the strategy is the same. You prove concentration of mass. How? You solve a PDE, which is almost the PDE you started off with, except for the addition of this. Right. So that's not trivial. Huh? In the deformed Hermitian-Yang-Mills case, even this part is difficult. It's not trivial. Then you produce a current that satisfies the cone condition. Then regularization is again very similar. Watsky, this Gaussian type argument. Again, the induction hypothesis and so on. This part is roughly, it sort of carries through more easily. This requires some work. Okay. Requires a lot of work in the deformed Hermitian. Again, in the projective case, my student could do it using this trick a little more easily, but in the non-projective case, I mean, Gaussian's original work notwithstanding, if you want to get rid of this uniformity that was done by Chuli and Takahashi, and again, they had to put in some work to do this concentration of mass business.
Further questions?
So let me mention one problem that's still open. That problem is the following. If instead of this equation, suppose I give you what's called a Hessian equation, that is omega raised to p chi raised to n minus p is chi raised to n, for instance. For example, when p equals 1, this is just the Laplace equation, more or less. This problem also has a numerical criterion, and this is still open. Ideally, we would like to follow the same strategy. The problem is this whole business about Lelong numbers for non-plurisubharmonic functions and Sewell's theorem, all of those are still open. We don't know them yet.
So can't you show that solvability is independent of choosing chi in its class, and then just kind of think of omega as fixed and chi as the variable? I mean, here omega is the variable, but you could think of chi as the variable, solve for chi, then show actually solvability was independent of choosing chi in its class.
You solve for chi given omega.
So omega is your unknown here, but if you can just solve for chi first.
Right. I see. So you prove that the solvability is independent of this, and you solve.
That could be hard. I should say.
Yeah, I don't know how one would do that either, but
fix that by with coercivity of some energy function.
Right, that's right.
Kind of goes out all conditions for energy functions.
Wait,
But,
is that the case? So wait, so suppose are you right that if the solvability of this is dependent only on the cohomology, these classes, if you give me a chi, I want to find an omega. And what you're saying is you fix an omega and you'll find a chi that solves this. I see. And for such a chi, this omega will satisfy the cone condition. Maybe that might work. I don't know. You're right. Is that independent of? Yeah, maybe that's a strategy. But then you have an even more generalized version of this. That's when you add this as well. Then you're screwed, right? I said but yes, I mean, why would you, honestly, I don't see any reason to care even about this one. I don't know any examples where this sort of a thing pops up. So at least in the cases people care about, this conjecture has been solved.